Welcome to 61st lecture. We're studying circuit analysis, and in this lecture we'll study delta connected load and delta connected source. Right, we have this delta connected source driving a delta connected load where these are the line voltages 215 at an angle of -10, -130 and -250. It is driving a it is driving a load that is 9 plus j6 ohms and in each branch, and it also delta connected, and we have this 0.05 plus j zero point 0.1 ohm line impedance, the impedance of line that is taking this voltage to the load. So we have to find this line voltage VAB. This is what is required. So we'll identify a loop here to make things easier, this loop, right? And we'll write a KVL equation for this loop. KVL, Kirchhoff's voltage law equation for this loop, right? We know that the voltage rise is this -215 at an angle of -10 plus across this line impedance we have a voltage drop, and across this line impedance we have a voltage drop, and across this line impedance we have a voltage drop. But it is important to note that the currents through all these impedances are different, right? What are the different currents? IA is the current flowing through this branch, IP is the current flowing through this branch, and since we are assuming a current clockwise, so our assumed current would be opposite to what IP is. It would be negative of IP, right? And the current flowing through this 9 plus 6 J6 ohm resistor would be the phase current. Why? Whereas IA and IB are line current. So phase current should be square root of 3. One line current divided by square root of 3 and should be lagged by 30 degrees. So this is important to note. And then we have written this KVL equation, which is IAB is the current flowing through this 9 plus J6 ohm impedance. This is IAB, and this IB is opposite to what is the direction of our desired current. Therefore, we'll put a negative sign here. Right, so IAB is actually IA multiplied by a complex number, which is 1 over square root of 3 at an angle of -30, because to make it the phase current, because this is the phase current and this IA is the line current. To make it phase current, we divide the line current by square root of 3 and delay it by and lag it by 30 degrees, -30. Similarly, IB is also a line current. IA is also a line current, but IB is delayed by 120 to fulfill the requirement of balanced three-phase system. So now we have computed IAB and IB in terms of IA. So we can put these values in, in equation number 1. We'll put this here and IB here. So putting these values will give us this situation, will take us to a point where we have these complex numbers. So we have to actually multiply these complex numbers first. So we have to take them into polar form to multiply. We have converted this into a polar form to multiply, and once this multiplication is over, then we can convert them back into their rectangular representation so that real parts can be added in real and imaginary into imaginary. And then finally, this number is converted into polar form to compute IA. IA is the line current. So we have to find the voltage drop across this C delta, but the current flowing through this 9 plus j6 ohm C delta is the phase current, IAB. So let's compute IAB using this formula. So IAB is IA multiplied by this complex number. It gives us this IAB. And once we have computed IAB, the current flowing through this C delta, we can apply Ohm's law. We can apply Ohm's law and multiply this with C9 plus J6 ohms, which gives us 214 at an angle of minus zero point 0.9. Right. So since we are asked to find out the magnitude of VAB, that is equal to 214 volts. That's all for this lecture. We'll continue studying more about three-phase systems in our upcoming lectures. Thank you.